begin MCMC today. We'll just take some baby steps into that. Anybody concerned, overly concerned about a midterm coming up or anything like that? Start to figure out whose personality is which in the class. So lay it on me. Or, oh my goodness, what's going to be, what is on there? So I will give you guys ample time to dissect what's going to be on there. We'll do a review session tomorrow. We'll do a review session next week as well. So, no, not next week, the week after that. So next week, we'll be taking another 3-day weekend. So no review session on that Thursday, but this Thursday we'll do a review, not next Thursday, then Thursday after, and then you have a midterm the Monday after that. So if you can keep track of all of that, you're probably able to do pretty well on this midterm. Any great concerns so far? Yeah, we've got a couple minutes where we can review some concepts. So why doesn't somebody just like spout out a distribution before we jump into MCMC stuff? Markov chain Monte Carlo, how do you computationally learn what the distributions of these parameters are jointly, conditionally, marginally, without having to do a bunch of math? You know, how do you use a simulation technique to do it? So probably to learn probabilistic distributions, it's not unreasonable to use a probabilistic device. So I won't say that it's not unreasonable to do quadrature or something like that. Anybody know what quadrature is?
It's kind of like a discrete integration, I think.
Yeah, it's like a discrete integration. It's like a discrete continuous integration. It's like both of them, right? So in high dimensional space, instead of writing the whole function down and integrating over it and doing all the math, you approximate that function with basis functions. So one such basis function are straight lines, the linear basis function. We usually have a name for that approximation. Does anybody know what the name is? When you integrate it over that sort of thing, we got a name for it. The Riemann sum thing. You'd have the left endpoint and the right endpoint, and if the function was increasing or decreasing, you could put a bound on things. Teach you the left endpoint rule, the right endpoint rule, then the center point rule. So, geez, why didn't you just like pick every possibility? The golden ratio rule, you could have moved it over. I don't know if that would help. Probably not. That's called a histogram. So it's a histogram approximation to a function, is what I usually call it. So a histogram. So basically just take some points, evaluate the function. So I could take samples and make a histogram straight out of it. Or I could take a function and make it look like a histogram instead by using a stepwise function. So you might call it a stepwise sort of function. Very important concept if you're a real analyst or something like that, a mathematician, because you can use those concepts to prove almost anything. You just shrink down those windows to epsilon and show what it converges to. And if you lived in the 1600s, you could have convinced yourself about calculus and been notable for all of eternity. Later on, they teach you about using things that aren't straight functions. You can imagine if you have a super wiggly function, the straight line approximation isn't very good. So they let you put some curves in there. So you use quadratic function, parabolas. Anybody remember what that rule was?
Simpson's rule?
Yeah, Simpson's rule. So that was Simpson's rule. It's got the 2's and the 4's in there. So I don't remember exactly how it works myself, but I kind of remember, I could remember it in probably 15 minutes on Wikipedia. So, but it's a parabolic approximation to things where you're using little parabolas everywhere to approximate the function. And it makes a smoother function, which is kind of nice. So now you can start doing calculus on things, which is kind of cool. MCMC is kind of like that. Sampling techniques are kind of like that, but instead of using these, basis function approximations, we sample out of the distributions and we get points from the distribution that represent weights. And the more points in an area we sample, the more weight we're putting in that area, which is basically akin to the height of that straight line approximation or the parabola. So it's called Monte Carlo when you do that. You sample out of the function, and then you use those samples to approximate the function. by maybe making a histogram, something like that. So, or at least representing it visually. You can do anything you want with the samples. So you probably wouldn't make the histogram and then use the histogram approximation. You use the samples directly. So that's Monte Carlo. Does anybody know what the competitive advantages of Quadrature versus Monte Carlo are? You could do either one. So there are two different, I kind of see after many years of thinking about it, it's probably sometime in grad school where I'm like, I can see these things as the exact same concept, although mechanically they're different. But conceptually, it's the same thing to me. There's trade-offs. Why would I do one versus the other? I'm a Monte Carlo guy. So, could have been a Quadrature guy. I was a Quadrature guy first. Does anybody take numerical analysis still? Does that happen? Yeah. So you know what? There's other techniques.
I was just saying yes to take numerical.
Oh, yes. Yeah. Yes. Like numerical analysis. It's pretty cool. So you learn all about Quadrature. Different Quadrature techniques, different basis functions. You could even use Gaussian bells and raise them up and stuff like that, and that's kind of nice. So Gaussian sort of approximation to something. Those tails inflecting out gives you the ability to make things even smoother, which might be nice. So there's splines that you'll learn about in your numerics classes, and those can come up, make functional approximations. You can come up with integration techniques. So some of the nice things about splines, well, let me ask the people that took numerical analysis. What do they teach you is like cool about using splines?
Capturing nonlinear relation.
Sure, you could do that. That's true. So any of these, like even the linear basis function thing, you could build splines out of it. And using these like even flat functions, the most linear, uninteresting linear, we won't even let you tilt. You could come up with a trapezoidal sort of rule if you wanted to. But if you're like that, you could capture nonlinear dynamics. There's limits to it, how smooth it would have to be and how many little pieces you used. So in numerical analysis, they don't just teach you how to do it. There's something they test you on. And when you see people present that are numericists, they always are doing the exact same thing. Numerical analyst wizards?
I'm thinking right now, I'm not a wizard.
What do you do with it all? Like, you have an approximation, what's the next question?
Error.
Yeah, how good is it? So, how good is your thing? So a numerical analyst, it's not their job to just go, well, a little wiggler. And that should be good. You know, more flexible. That's great. That's a good idea. Write the paper, done. Oh, everybody thinks that. No, you want to know about the error rates. So under certain conditions. So they're able to quantify the error rates on everything, that the error is within this. And they usually make an asymptotic statement about how many data points you have that you're using in everything to estimate the function. So they'll say, like, it's as good as like n squared. Something like that. So they'll make these statements about the error in terms of the number of points you have. And that's what you spend all the time getting tested on. Can you do the technique, and do you know what the error rates are? So all these functions that are a little bit wigglier, obviously they can do some math on them in advance and figure out what the asymptotic error rates are. And know that asymptotically, one method works better than the others. So what people will do, take it a step further, is let's say I have a function that's super wiggly over here and pretty smooth over here. So I need to use more spline approximators, more knots, things like that, over in this part of the space than I do over here. So then you have adaptive methods. And so that's kind of hard to do. Sampling kind of does that automatically. If the function is got a lot of action and height over in a part of the space, it's going to put more emphasis there by sampling more out of it. That's what more height means. So, and hopefully, if it's wigglier, you might spend more time there too. And so there's techniques like that that are built into Monte Carlo. So there, all these ideas can go back and forth. But we haven't answered the question, what's the competitive advantages? We see stylistic differences. The errors. It's all about the errors. So I'll tell you something, I'm not going to prove this here, but in 3 dimensions or higher, so 3 is that break point, Monte Carlo has a computational advantage on splines. And here's why. Think about it in 1-dimensional space. If I wanted to learn about that space in 1-dimensional, I just need to chop it up a little bit. And I can kind of do a search on that space and I could find anything in that space. So here's a true story that happened to me. Once upon a time, I wasn't buying my parking permit. Who does that and tries to like hide their car somewhere on campus? So I now buy my parking permit. So I spend like $500 a year on parking permit. So, but I was parking, you could go over to the Wright House over by the duck pond and park there. Nowadays, this is like 15 years ago. So nowadays that parking lot's full before anything else. So, and I was walking and I had a bunch of stuff in my hands and I was thinking, what do I do with my car keys? I had my car keys and let's see if I have real keys. So I had my car keys in my hand and I'm carrying all this stuff and I decided to do this with them. So I'm walking across the lawn, right over there, whatever that little quadrant is that connects the duck pond out to whatever that road is. I'm walking through and lo and behold, no surprise, I get up to my office with all my stuff. Obviously I was in a rush already. So this is when you make these mistakes. And I'm like, no. So if it was a straight line and it was a 1-dimensional search, here's how I would search for my keys. And I would find them. So pretty quickly. Unfortunately for me, that was a 2-dimensional space. So I couldn't actually look at the space because it was in the grass.
Maybe even slightly 3-dimensional.
Yeah, a little bit 3-dimensional too. So we'll treat it like a blind 2-dimensional surface. That's at least my approximator to it. So look on a 2-dimensional manifold maybe. So do some proofs while we're at it. And so I'm like trying to do this line search. I think I walk this way, let me walk over a little bit more, and one of my peers finally comes out and is like, what are you doing? And I'm like, I'm looking for my keys. They've gotta be in here because I didn't hear them drop. So it's gotta be in the grass. And after 15 minutes, we finally, here's the keys. My friend found them, I didn't find them. So thank you very much to Eric for finding my keys for me, but it was computationally very expensive. You can imagine if we were in a 3-dimensional space and I couldn't actually visualize everything until I was at the point, like when you do a functional evaluation, you don't know what it is until you go to that point and you evaluate it. So we would have been there forever. So how hard is the problem getting as the dimensionality increases? It's exponential in the dimensionality. So if I have a good approximation with 10 points on a line, then I would need 100 points to have the similar sort of resolution in a square. And I'd need 1,000 points in a cube, and so on and so forth. So when you think about quadrature, that's what you have to do, is you have to basically bin up that space and chop it up. Where Monte Carlo spends all the time automatically by spending most of the time by sampling out of the high density stuff. So it spends most of the time on the stuff where all the action and the distribution is, the height, the wiggly stuff, lots of variability. Now I'm telling you kind of a fiction. That's at least hopefully. So if you have a perfect sampler, you can do that. So once you start sampling from, let's say, what's called the target distribution, then that's true. Usually the algorithms are adaptive in some fashion, and you have to hone in on where the action is. You don't know where to even start. You have that curse even worse in quadrature. So you wouldn't know what to evaluate in the first place. So I'm going to say if you are one of those people that's trying to do an exploratory technique, MCMC is very good for that. If you're around people that require errors where you put tolerances on them and you don't want to quantify Monte Carlo error, probabilistic error, you could do an exploration using MCMC and then a refinement using quadrature. And so you could even do it the other way around. You could do something kind of like MCMC. If you've ever heard of variational Bayes, it's empirical Bayes on a variational approximation to the posterior. Anybody ever heard of anything like that? Anybody know who our invited guest is this week in the stats department? Tamara Broderick. What does she work on? I just gave you. And you know what hint I gave you, so yeah. So I bet tomorrow you'll know certain answers to these sort of things. We do a quiz show in the department. So I'm going to bake in some of her stuff, and she does variational approximations to things. So you could do that. It's very fast. You could build your MCMC to get better refinement, and then if somebody wanted numerical approximators, you would know where to build the grid in the first place. So I think you can use all these tools together. I happen to be an MCMC person. I write papers on MCMC. I like MCMC algorithms. I like the flexibility of them. And some of it is fashion. But if I work on high dimensional problems, I need things bigger than 3 dimensions. I get a lot for free out of all of that. And I don't work around communities like physicists that say, oh, we need to quantify it in terms of asymptotic numerical error. That's a choice. I don't think one is better than the other. It's just a preference, what you're used to. Sam?
So I'm just a little bit unclear on if you're doing a quadrature technique or a Poisson's technique, or you're not sampling,
Yeah.
you're not, okay.
They don't.
So what are you doing now?
They're chalking up the space, gridding it up,
Right.
basically, if you do quadrature.
Right.
So, and they grid it up and they evaluate the function at all those points.
Right. So this is assuming that you know the function.
Yeah, so we're gonna assume you know the function. So that's not a hard assumption. We're gonna build a model, we're gonna have a function. And for a Bayesian, our function is gonna be likelihood times prior. We don't even have to worry about the normalizing constant. So I'm gonna hand you F. In a Bayesian class, F is the posterior. I guess I've been calling that pi for a while. Yeah, so you get to evaluate the function. Sampling from a function and evaluating a function are different things. So let me just give you an example. So I think sometimes people are confused about what they can do with a function. Just because you have a function doesn't mean you know anything yet. You just have this thing written down. So sampling from that function is harder. So let me just say, if I gave you this function, e to the minus a quadratic form, could you evaluate it? Can anybody not? To us, we almost take it for granted. I just go to MATLAB.
The
Or,
computer might have to
Yeah.
do a Taylor approximation.
Exactly. So there's something it's doing. And we could probably do the Taylor approximation too. So E's not hard. So we could do that, and that's probably what it's doing, is some sort of Taylor sort of thing. And they could even give you error rate on that that is smaller than the computer precision. So no problemo. These are kind of like what I would call solved problems, or at least problems that we're familiar with from calculus class. But yeah, you could do it. And I'm not asking you to do it on paper, like could you do it? Somebody says, go run off and evaluate E. You know, of course, back in the day, that was a hard ask. You need books with tables. What did computers look like? They were stacks of tables. So those were fun days. So we're past that. So yeah, you could evaluate it. Could you sample and give me normal samples? 50 normal samples. You could probably do that too, but you realize you don't know what that function is doing maybe. So what it actually does on a computer is if you sample 2 uniforms, I can give you transformations of those 2 uniforms that are normally distributed. And I can prove that. So you can transform directly uniforms into all kinds of different samples. So we might want to study a technique or two like this before we go too far into MCMC. So a lot of times I just jump straight to MCMC, and we don't even know what Monte Carlo is. So maybe we need to take a break for a second and see like how some MCMC techniques work.
Are we going to talk about that transformation of uniforms or?
Yeah, we just did.
Oh,
It's
yeah.
called Box-Mueller.
Oh, okay.
So, and it does a transformation. You need to evaluate some sines and cosines. So, you really just need to evaluate the inverse tangent. So, and you need to evaluate some logarithms. So, I'll write it down for you next time. I'll show you what the transformation is, and if you want to do the transformation, it's just one of those Jacobian problems. So So you work out and you show that the transformation of variables in two-dimensional space is normally distributed when you set up the transform just right. Does anybody know what the transform is off the top of their head? Has anybody ever seen it? We'll glance at it maybe next time and just write it down, talk about what the steps are, but I don't think we'll fill the whole lecture. So we might talk about one technique, inverse CDF. I know a bunch of you have brought that up before. That's one such technique. Limits to the inverse CDF technique are that you need to write down the CDF and you need to be able to invert it. So the CDF means you have to evaluate the PDF, integrate over the PDF and write it down in closed form. Can you do that for a normal? You cannot. So it's always that ERF function. So that you get like that air function thing is a normal distribution. So it's like, what is that in like MATLAB or Mathematica back in the day that it's like ERF? Oh, cool. I don't know what that means, you know, but it's e to the minus quadratic form. So, or it's the integral of that. And you can't evaluate it explicitly, you can do a numerical approximation to it. So you can sample from that function explicitly though, perfectly. MCMC is a little bit different, where what we're going to do is we're going to walk up the tails of the distribution until we find where the mass is. And while we're making the run into the mass, and we're iterating through the space, we haven't learned what the distribution is yet. And so once it arrives at the mass of the space, then the samples we're going to get are associated values from the posterior. So if I took all those values and I scrambled them, and I shuffled them, then they would be samples from the posterior. They'll be Markov related to each other, so they're not independent. And so, but in this non-independent fashion, we'll be learning what the posterior is. So I'd like to get into that lecture. But let me just ask you before we go too far down into sampling, where we're going next. So I think we just talked about quadrature versus Monte Carlo. So just a discussion on why some people like Monte Carlo. I'm not saying that quadrature is invaluable, but in high-dimensional spaces, and now everything is like, at least we don't even call it 4D high-dimensional anymore. It used to be back in the day, you said 10 and people would freak out. Have to compute a 10 by 10 covariance matrix? That's a big deal. So invert a 10 by 10, ever try? Let me just ask this, do you guys know how to invert a 10 by 10 matrix? If somebody asked you to develop an algorithm, what would you do? I'm not asking you to do it by hand because I already know none of us can do it. We would make way too many errors along the way.
You choose like Gaussian elimination.
Oh, okay, I gotcha. So you would do Gaussian elimination and pair the matrix with the identity.
Yeah.
I love it. I love it. That is definitely the way they teach you to do that in your first linear algebra class. That's how you learn what the inverse is. So that's true. That is. But computing-wise, can anybody answer why you don't actually usually do that?
It takes forever.
And it's numerically unstable. So you have like weird numbers in there. So if you look at A times A inverse, you know, your computational evaluation of it, it should probably be the identity back. But if you actually do that with some weird funky matrices, ill-behaved eigenvalues in there, so eigenvalues that are close to 0. So it'll mean that the computation, your way of doing it using Gaussian elimination, you divide too much doing it. So maybe not the best technique in the world, but conceptually right. So, and people didn't know this until they started using computers and trying to do this and going, all these ways we teach people to do it don't actually work well in practice. So anybody have any other techniques? Iterative techniques. Does anybody know any iterative inverse solving techniques? Didn't people take numerical analysis? How about Gauss-Seidel? Jacobi? What's that? So Anyway, you basically do these iterative one-row solves on things. You can do them very, very fast, and you can do them in very numerically stable ways. So you don't have to do everything at once, solve the whole joint all at once. The whole matrix, you can do it sequentially and stably, and that can be very nice. So you might have intended that and said, oh no, I actually factorize my matrix first into a QR, and then I do Gaussian elimination in disguise, you know? And so maybe you do something like that. We'll talk about all these issues since we're getting into computers. I will say this, if you're ever touching density functions and you're not working on a log scale, you're about to make huge errors. So all the code I've written for you doesn't scale well to high dimension or big N if it's not on the log scale. So that's my first numerical trick I'll teach you. So these things will be popping up in your homeworks in the future. So if you haven't learned all these lessons yet, you'll probably encounter a few of them in the homework. So try to give yourself some ample time so you can go and spend a few days talking to each other and going, I keep getting inf. You know, what is going on with this thing? So not an uncommon experience the first time you get into this. We'll try to cover some of those issues. Let's just take a side step. So, and just do a little review before we jump into all this new computational stuff, and just talk about some distributions. Let's talk about a Poisson. So xi is Poisson distributed. Does anybody know where that name comes from? If you're in a French restaurant and you see this word, what does it mean? Fish. So this is the fish distribution, right? This was originally incarnated by somebody that was counting fish. No. This is a person. So this is a mathematician. So you can think about this distribution. Here's a fact. The Poisson distribution is kind of like the binomial distribution with a limit on n and p. So I'll just say binomial n and p as n goes to 0 and p goes to infinity. So this is like a counting model, and something else has to happen simultaneously. N and p have to converge to something finite. So if p goes, oh sorry, this is the wrong way, right? That's why you guys are pretty good. So that's an easy limit to take. So this goes to 0. So other directions. N gets big, the counts of things gets big, and the probability of those events becomes exceedingly rare. And this is a finite value, so they do it in some rate where this doesn't explode or slam into 0. So not 0. And we're going to call that lambda. And this is this same parameter right here. So that's a Poisson model. So sometimes people will think of these as rare event models, where you're counting lots of stuff. If you want to learn about anything that's rare event, you're going to have to count a lot. So no way around that. King knows. So kind of makes sense. So rare event models, you can think about them that way. So I see a lot of people do this sort of thing, and they go, well, it's kind of a rare event. There's also a few other things. I'll just mention that the variance of the exponential is equal to, or the Poisson is equal to the expected value. So this is lambda as well. So this parameter right here is the mean and the variance. So it kind of has this co-interpretation. Let's think about if that makes sense. If I were counting stuff, would I make more errors if I were counting just a few things or a lot of things? So this says as the counts go up, the variance in your counting goes up. Kind of makes sense. Yeah. When somebody like throws down, you know, I go to the store and I pull out like 3 Ditto honeys or something like that out of the bin, and I throw them down. Let me get those 2. They don't ever count. They're not like 2, You know, they're like 3. Okay, you got 3 of those, 15 cents. When I throw down 7 of them, it's comical. You know, people can't count 7 on just sight. They're like, wait a minute. You know, they sort them out. So people make mistakes when you count more. Question is should this be constrained like this? So some counting processes, the variance can be higher than the expectation. You might ask this question, can it ever be lower? And I will tell you this, not in the exponential family, it can't. If you ever are counting something and the variance is lower than your expectation, it means you have a mixture of Poissons. That's probably what's happening. So you need to use a mixture of distributions. That can be proven. So if it's going to be this nice distribution that's not a mixture, multimodal, the variance has to be bigger than the expectation. So sometimes you have distributions where the variance is larger than the expectation. Does anybody know of any distributions like that?
Negative binomial.
The negative binomial. So I'll just mention that. Negative binomial. He has some parameters too, N and P. This is a distribution that's asking about counting things, counting the number of trials until some number of successes. So let me not make this K. Let me not make this N, let me make it K. So K might be something like 5, and I'm asking how many times do I need to flip a coin before I see 5 successes? So that's how we could interpret it. Or how many failures would I see before 5 successes? The failures plus the successes plus the failures is the total number of trials. So in some sense, dealing with one is dealing with the other. I will point out, be careful when you look at books, because sometimes they'll reparameterize on you. So the negative binomial is over-dispersed. So this means the variance is larger than the expectation. This is dispersed just right. And then there's under-dispersed. So when the variance goes lower than the expectation. So nothing in the exponential family is under-dispersed. Mixture models are under-dispersed. So I remember the first time I saw a problem like this, and my teacher gave me a set of 20 data points and described it as the number of car crashes in an intersection, and said to model it as Poisson and to do an analysis. And I came back and I said, the variance isn't even close to the expectation. And she's like, yeah, it's close enough. And I'm like, they're like 10 apart, you know, and the counts are like 15. That seems like wildly different. It's like several standard errors out. So, and are we sure these car crashes are independent? And so she said, I just sampled the numbers out of a Poisson. I made up the problem. It's not a real problem. So then I thought, oh, okay, then I can do it. So, but I thought it was a modeling question. So anyway, check all those things. If you ever see anybody say something's Poisson and you check, I think you should go back and ask. So that's just a little bit about a Poisson. Let me tell you what the probability distribution is. This is the mass function, xi. You know the way I like to write it, given lambda. So there's one parameter in this model. Just get that out, just because it's a direct distraction. Somebody help me out. What does this distribution look like? I'll do the easy part. Lambda to the xi. Xi factorial. And if you know what the Taylor expansion of E is, this will make sense to you. So what the normalizing constant is. So in terms of the probability mass function, that's the normalizing constant. But for a Bayesian, that's part of the kernel of the likelihood function. And this part doesn't matter. So for a Bayesian, they forget about that. And they think about this function because it's a function of lambda that they're going to use to form the likelihood function. And so just be careful about what we think about as the normalizers. I will say I am wildly relieved being a Bayesian in some sense that I don't have to worry about this thing right here. Because I can just log my way out of that. But factorials, fine, I can use Stirling's approximation or I could use something and go, it's supposed to be good, right? So nobody ever checks this stuff. This is a monster to compute. So on a computer, how big of a factorial do you think you can compute before your computer can reliably tell you what that number is?
In the floating point?
Yeah. Yeah, so you probably are going to ask me next 16 or 32. Let's say 16. That 32 stuff's pretty important these days. We all have 32 these days, right? We don't even know. That's how spoiled we've got it. It used to be like, geez, I'm going to have to spend a lot of money because I can't compute 52 factorials. So the number is like, it's like 60 or something like that. 32, now I have to make the numbers bigger. So to make my point, but it's not more than like 110. So it's way less than that. It's not double because this number has kind of an exponential thing going on. So anyway, if I were going to form the likelihood function, I get a whole bunch of data points. I'm just going to write this thing down. So this is proportional to I goes from 1 to n, e to the minus lambda n. I'll just leave the n out since I have the product there. Lambda to the xi's, and that's just e to the minus lambda n, lambda to the sum of the xi's. Lo and behold, all you need to know to compute this distribution, or at least its likelihood function, and that's all the Bayesian needs to worry about, is all you have to hold on to is the sum of the xi's. So this part does not help you, so you don't need to compute. So what you can see is that this part isn't next to any of the lambdas. You can't untangle it. You can factorize out the xi factorials, so it's part of our constant that we're throwing away, and we're not throwing away any lambdas. So let me just ask a question. What's the conjugate product? Not too many choices here. You stare at this thing and you think, as a function of lambda, what the heck does that look like? What could I multiply it by to preserve its form? It's a gamma. Yeah, so that's it. It's a gamma. So this thing has an entirely familiar form. You'll get a gamma posterior out of this. It's very easy to work with. Let me ask this other question. So this is a gamma. Given x, this is going to be equal to some gamma distribution. And the name of the game is you identify those parameters. So you probably start with a gamma alpha beta, and then this is going to be some gamma with some updated parameters. Give that problem a try. Make sure you can do it. So it'll probably come up in the future, or something eerily similar to it, maybe midterm time, maybe on Friday. We'll see how we feel. So I think we can all see that. So what's going to get added in right here, it's going to be the alpha minus 1, and that minus 1 will be hanging out there just for free for you, because it came from the gamma prior. And this is going to get added into the beta term. So n plus beta will show up. You know what the expectation and the variance are for a gamma? It's alpha tilde over beta tilde, or alpha tilde over beta tilde squared if you're computing the variance. So you could tell me all kinds of stuff all about this. How about this? What's the posterior predictive? So if I'm going to predict a future value, given my previous values, and I don't get to know what lambda is, I could guess at lambda, and what better way to guess at something than to guess multiple times and put weights on it. So, integral f, well, what did I use? PR. So this could be a PR if you wanted to. Probability. xi given lambda times my posterior distribution d lambda. Where do I integrate lambda? Lambda's positive. I don't think I said that yet other than right there. So if it's the variance, it's got to be positive. If it's zero variance and that thing were zero, it's just a point mass at zero. That's got to be the least random variable there is. I guess it is. That's fine. Sometimes people will make mixtures of Poissons with Poisson and a point mass at zero. That's the same as another Poisson with lambda being zero. It's called the zero inflated model. So sometimes you see an overabundance of zeros and you can deal with mixtures. We will deal with that in this class, we're just not there yet. We're just inspiring the concepts. What distribution is this? Take a guess. Jared?
It's a negative binomial, but I'm not sure what the parameters are off the top.
It is a negative binomial. So was anybody else thinking any other distributions? T?
T, I think.
Okay, so T, that's one possible answer. Josiah?
I mean, I'm going to say it's stupid, but I tried to do exponential.
Exponential. Yeah, exactly. No, I really appreciate that. So it's like, we already know those answers are wrong, but we're going to throw them out anyway. Let's do a quick check. How can we rule those out? Let's think about this thing. These are all data points right here. These are all your x1s. I think that's the best way to practice, is be willing to just face plant that thing. So you learn from it. So these are all xi, all counts right here. So each one of these is a count. So what are these numbers? They're like 0, 1, 2, 3, 4, 5, things I can do with my finger. Yeah, so Josiah now has omitted his answer. It's not exponential because an exponential lives in a positive continuum. So at least we got the positive side, but that's a continuous space. So this has to be a discrete distribution. So T, same reason. T's, live on minus infinity to infinity, the entire continuum. So we're kind of thinking, what other discrete distributions do we know? There's only one other one we've discussed in class, and that was about 30 seconds ago. So how could we not know that? But it's the negative binomial. What are the parameters? If you're able to recognize the expectation and the variance of everything, you'd be able to do it real quickly.
It kind of makes sense too, because if you had the variance used to be equal, if we're adding hyperparameters now, our variance is going to be higher.
Thank you so much. You did the iterated variance form in your head real quickly. Let's just go into this real quickly. So the variance of x tilde given x, just since we're practicing and we're seeing if all these ideas are semi-fluid, we knew what to do. If you wanted to just check this thing is over dispersed, you could just do this. Expectation of the variance of x tilde given lambda in x plus the variance of the expectation x tilde lambda in x. Let's chisel away real quickly. What's this thing right here? We don't need that. That doesn't help us in the wrong one. Unfortunate choice I made. This is a lambda, this is an x. in the presence of lambda, the data doesn't help us. This is an IID distribution. We know the variance of this. This is this thing right here. That's a Poisson, and we know what the variance is. If you're familiar with the Poisson distribution, that's just lambda. So plus the variance of the expectation, that's a Poisson distribution too. My notation's incredibly sloppy. But that thing's not helping us because that's just the sampling distribution, that's that as well. So let's keep our notation tight and make sure we realize this is a posterior distribution. We're still conditioning on the x's in all of this. And usually I write that in here. So everything's conditional on x because we're conditioning on x. So every operator gets x in there. And that's why I like to keep that notation in there. Otherwise, when I get down here, I might forget what that represents. So now that's the posterior. That's this bit. And we know all about our posterior. It's some gamma distribution. And we could even write this down right here. This is going to be alpha tilde over beta tilde squared. We haven't worked through those calculations, but I bet you could do it. And this one is alpha over beta tilde. So these are just my posterior calculations. My old variance was this, and now I have a little bit more. And that's what Josiah said. He recognized that quickly, that, oh, the variance goes up in the prediction, which is good because predictive quantities always have some variance attached to them. So you can never get rid of it. There's uncertainty in what you're going to see because the process has uncertainty to it. All you can learn about is your parameters. And the bigger n goes, the smaller this thing will be. And that's going to be going smaller quicker than that thing. So the data will help you to learn this thing, and that thing will be going down towards 0. And you could check all that. What about another distribution? So this is what I think you should be doing in the run-up to the midterm. Think of a distribution, see if you can work through its conjugate analysis, identify the expectation and the variance, and maybe think about the predictive analysis. This is a negative binomial. We would have to work through that integral to figure out the kernel of that was negative binomial. What does a negative binomial look like? You should probably look it up if you haven't been exposed to it. I don't think we're going to touch it a ton in this class, but it's still a good counting distribution that's over dispersed. So it's a powerful tool for your future, and it's something that comes up with predictive analyses. So even if you like touching Poissons, you're probably going to touch a negative binomial. A way to think about this negative binomial, so I didn't have to think about this as a posterior predictive calculation. This is just a mixture of a Poisson with a gamma. So I'm mixing over that rate parameter. And that's all we're doing. We're averaging over that parameter in some sense. And that's the way I see this equation right here. And so negative binomial distributions are scale mixtures of Poissons with gammas. T distributions are scale mixtures of inverse scale mixtures of normals with gammas. Inverse, it's on the precision scale. So it's what we're mixing over. So that's kind of cool. So we're starting to see trends right here. So these are scale mixture models. And we can add them together and make additive scale mixture models. Taking two Poisson distributions if you have two clumps of data in different places, dealing with maybe the under-dispersed problem. So now we're starting to learn modeling tools. How about exponential distributions? I bet you guys could do that one pretty quickly. And the reason why is an exponential distribution, I'll just write it down real quick. Just looks like this, e to the minus lambda x lambda. And if you like flipping over your lambdas, that's fine. We can transform back and forth. You do your probability calculation, I do mine, and we do a transformation of variables. So I like this one. Exponentials look exceedingly gamma. So just keep in mind, we don't have to remember quite as much stuff right there. So they look like a constraint on a gamma distribution. So depending on which scale you put it on, it's very common for people to flip this thing over. That's your -1 if you're searching for it. And they're putting it on a different scale. So I like putting it like that. So it's a matter of convention. But what's the conjugate prior for an exponential? It's a gamma. So you're going to get a gamma out. A common mistake would be it's an exponential. I bait half the class on that if I don't front load. You jump to an exponential, right? It's actually a gamma because what you get out of it is not an exponential anymore. It's like modified and it looks more like a gamma. So exponentials and gammas have connections. And I will tell you this, exponentials and Poissons have connections, and that's not that surprising if you just stare at these forms as well. And so here's a fact, that if I'm waiting for things to occur in these rare event models that could be distributed, Poisson, the time between their arrivals is exponentially distributed. So the waiting time in Poisson models is exponential, and you could prove that. I'm not going to say that should be obvious to you. I'm not going to ask you guys to prove that in class, but it's in most elementary probability books. Or I should say stochastic process books, and that's the foundations of stochastic processes. So that's called a Poisson process, where I'm just modeling the waiting time by lambda times t, where t is the time. So as t increases, it multiplies by lambda, I see more and more events. So you could even modify the lambda function, or modify what t looks like and deal with quadraticness, things like that. You can make it non-independent. You get a whole new field out of that. That's called renewal processes. So with more math. So what I like to do is use all of that stochastic processes to tell you about Markov chain Monte Carlo, and instead of doing a bunch of math, we can learn how to do a bunch of computation to learn about our distributions, so that we don't have to always do the integrals. So just keep in mind, if you were trying to get around this integral and you didn't want to write it down and you didn't recognize the distribution, I'm not saying that's the right thing to do, but let's just say you just, I just have a minute. My homework's due, I need an answer. So I could sample out of this, take those samples, plug it into this, and sample out of that, and repeat, and I would have things that are distributed negative binomially for free without even knowing it. Because that's my distribution, I can compute empirically the expectation and the variance, and compute computational. I actually did this on homework when I was in grad school real quick. I was like, I don't have time to do the integral, but I know I can get the answers in like 3 minutes.
So I'm going to go into this next the Markov chain, part of that implies that you are essentially taking an output and using that as information to an exponential.
Yeah, it's iterative, totally. So it's going to be iterative in that fashion. So it's an iterative algorithm, just like all iterative algorithms. The output from the algorithm becomes the input for the next step. And eventually this thing will converge. It's not going to converge to a point, it's going to converge to a distribution. I'm going to make you a lot of promises in this discussion to tell you this is true. We're not going to do a ton of proving. So eventually when I teach the Monte Carlo class again, that's where we would prove that the algorithm works and see real heinous cases of where it doesn't work very well. Next time I'd like to kick things off with a presentation on MCMC and then show you at least the idea of it, and then on Monday I'd like to implement some MCMC and show you some examples. So I think now's a good time to just kind of catch up on homework and concepts from the past, because you're just buckling up for the next couple days.
So we can include like the study materials on the MCMC?
Why not?
Okay.
Yes. Yeah, I gotta have something else to test you.